Hello guys. In the previous lesson we described the whole content of this course, and so the design procedure or the following stage or this stage are the guideline for completing this crank mill model. And so in the first place we should focus on how to create the free body diagram of the crank mill design in system dynamics perspectives. Okay, and so firstly we should create a model. We have now the model as like 3D dimension of this crank mill design. Okay, this is a sketch drawing. In here in the 3D dimension we have just like this kind of crank mill design in here, and so we have some white parameters at this moment, and so so this is attached to what? To specific wheel system. Okay, and so this crank is turning around the theta value like this one, and so this crank can be driven by the torque value and the theta value, and so the car is moving at the direction of the x in the positive direction. Okay, and so in order to create this model we should focus on how do we calculate the mass parameter or inertia parameter of this thing. In order to do that we should create a specific model in here with the shape factor and the material selection. These two are the basic elements to create a correct free body diagram and the 3D design in the real life application. Okay, and so we need to simplify this model in order to get a comprehensive understanding of it, and so we need to utilize the shape factor and the material selection by using this diagram, and so this wheel is the same as with this one, and so we need to create a 2D dimensional form of these things, such as for the shape factor we should state the whole length or dimension of these things like this one, and so in the front direction we have this kind of shape in here like this one, and so we need to give a specific dimension. Assume that all the parameters or all the shapes cylindrical for this study, but you may choose any shape for designing this crank mechanism, and so we should get the specific dimension in here. This dimension is equal to d1 radius, d2 radius, d3 radius, and this column or this mill is the same with this one, and so d3, d2 and d1 can be written on this 2D shape. Okay, and so d represents the radius of this system. Okay, and so in order to give the lengthening information, the L1 can be given in here, L2 given in here, L3 given in here, L4 given in here. L3 is the symmetric property. L2 and L1. This are the length of the cylindrical objects in here. Okay, and so the total shape factor can be described by using this diagram. And so what's our need to calculate in this design? And so we need to calculate the inertia factor, because the whole body is turned, not moving. In the real life it's moving, but according to or with respect to the car, we can neglect it. And so for more realistic modeling techniques, and so we need to add this m factor, or the meal total mass of the meal, into the last equation. And so in the final equation we should add the total mass factor into the last equation. Okay, and so in order to transmit the power or energy of this torque value given by the motor, and so we need to firstly calculate the inertia factor of these things. Okay, and so inertia can be considered as the for I1, I2, I3, I4, I3, I2 and I1. Okay, and so how can we calculate the total mass or inertia factor of these things? In order to do that, we should create the inertia factor with the basis of the what? The selection of material and the selection of shape dimension. And shape dimension is selected from the previous slide. Okay, and so the inertia factor can be calculated by what? I1. I1 is a cylinder, and so the inertia is given by the specific formula of the 1 divided by 2 times m1 times d1 square. And so the m1 is transformed into the what? 1 divided by 2 times rho 1. Rho is the density of this material, and so p d1 square, area of cylinder, and L1 is the length of this thing. And so this term creates the volume value, and so this gives us the material property. And so this whole term represents the mass of this factor, and so we need to times d1 square in the last place. Okay, and so rho 1 is a material property, and so the other things or other lengths represents the shape factor of this inertia calculation. Okay, with the same analogy, I2 is equal to what? 1 divided by 3 m2 L2 square, because this formula is different from the real one, because in the first place this is turning around the z dimension. Okay, or z direction in here. Okay, in the 3D dimension, and so this turning around in here, but the turn of the I2 is different from the inertia factor, because the center of gravity is different from this z direction, and so the calculation of the I2 is different from the I1. You should check the Wikipedia in order to obtain the specific information how to calculate the inertia factor, and so you can find the more useful information from it. Okay, and so this factor can be calculated by what or how? 1 divided by 3 times rho 2 times p d2 square L2 times L2 square. This is the M2, and the other things comes from the inertia calculation. Okay, and so I3 is given by M3 L3 square. Is a pointless assumption, can be used in here, and so the rho 3 times P times D3 square times L3 is a mass factor in here, and so L3 square should be added and at the end of this equation. Okay, and so I4 is equal to what? 1 divided by 12 and 4 dot L4 square must be equal to what? 1 12 rho 4 times P times D4 square times L4 times L4 2 or over 2 or square. And so these inertia factors are different from what this z direction affects every or each element differently. Okay, and so at this position for the D2 or material 2, the z direction is added, or the center of gravity is different from it, and I dirt center of gravity is different from it, and so the turning position is different, and so we get the different formula related to the calculation of the inertia factor. Okay, and so what about the R total inertia? The total inertia for the crank mechanism is given by 1 I4 because it's centered position in the crank mechanism, but in the other place each of the I1 plus I2 plus I3 should be multiplied by the 2 because the crank mechanism is symmetric, and so we have 2 I1, 2 I2, 2 I3, but only 1 I4 is included in this position because it's totally calculated by the inertia factor. Okay, this is our correct form of the total I crank formalization of the inertia factor. And so in the next lesson we will focus on how can we obtain the spring coefficients or the elasticity property of the crank mill design in the system dynamics approach.